Dr. Cameron Turner is a distinguished researcher and associate professor in the Department of Mechanical Engineering at Clemson University. He is a recognized expert in the field of surrogate modeling and has contributed extensively to the development of advanced algorithms and techniques for optimizing complex systems. Dr. Turner's research focuses on the development of surrogate models, which are simplified representations of complex systems that enable more efficient optimization and analysis. His work has been recognized with numerous awards and honors. At the Automotive AI Summit, Dr. Turner shared his expertise on the topic of learning with and from surrogate models. Learning with and from surrogate models is an important topic in machine learning because it addresses the critical challenge of optimizing complex systems efficiently. Many systems, such as those in the automotive industries, are too complex to be optimized directly. Surrogate modeling, which involves creating a simplified representation of a complex systems, enable more efficient optimization and analysis. By learning from surrogate models, machine learning algorithms can make more informed decisions, leading to better performance and faster development of advanced technologies. The application of surrogate models in the automotive industry has the potential to revolutionize the design and optimization of complex systems, leading to more efficient and sustainable transportation solutions. Therefore, understanding the latest advancement in surrogate modeling and its application to the automotive industry is essential for anyone interested in the future of transportation and the role that machine learning will play in its development.
Okay, thank you, Rahul. My name is Cameron Turner. I'm an associate professor of mechanical engineering here at Clemson. Most of my research ties into ideas related to surrogate modeling. You might ask, what is a surrogate model? And a surrogate model, in my opinion, is simply the ultimate black box of inputs and outputs with some uncertainty. So it's sort of like a close to a black box that we're used to seeing in controls and other domains. However, the surrogate model is really used so that I can take a little bit of data that I know and formulate that data into some sort of conceptual model that I can use to make decisions, whether I'm doing it with optimization, whether I'm doing it with analysis, or whether I'm doing it with some sort of intelligent agent. It's how it forms that perception of the world it's looking at. So as a result of this work, I've developed a couple laws that I'm going to share with you about surrogate modeling. The zeroth law is simply if it goes in, it comes out somehow, some way eventually. There are lots of different model choices available to you as a surrogate modeler. Everything from simple curve fitting, which we've all done in the room, response surface modeling, to my specialty is using splines as opposed to polynomials as the basis for modeling, but also we get into models like Kriging, radial basis functions, wavelets, support vector machines, neural networks, depending on the type of data and how we're trying to model it and what we want to do with it. The reason I like NURBS and splines as the basis is they give me certain architectural advantages that I can then leverage later on in my analysis to do optimization. So this is my nasty equation slide that I throw in. NURBS are really actually a relatively simple recursive definition that gives us a local polynomial with guaranteed continuity conditions over a global domain. And because of that, they actually have embedded within them their own surrogate model. That surrogate model is defined by a set of control points. And that control point network gives us the ability to do a lot of different things with surrogate models. For instance, in optimization, over the years, I've done a number of different problems in optimization, everything from working on 3D printed designs and coming up with different infill patterns that may give us more performance for the weight of the material or the weight of the part based on using models that allow us to approximate what's happening within the model, to modeling the global thermal coal trade to figure out the optimal duration of contracts to be negotiated between power plants and mines around the world. So a vast variety of scope ranging from global to very small local design questions. Now, the scale of optimization varies quite a bit over that scope, as well as the impact of uncertainty over that scope, but we've been able to use variations on surrogate models to achieve optimization results across all of that. One application I want to highlight is one I've done with the Navy Research Lab on their multi-axial robot testing machine, NRL 66.3. This is a Stuart-Gao platform that the Navy built to characterize nonlinear anisotropic composite materials on an as-built basis to determine their actual properties, not what was designed. It turns out the actual properties are not what was designed. So it's a room-sized 6 degree of freedom Stuart-Gao platform with another robot inside it to do multi-axial material testing to excite the coupled parameters within the system. The challenge of this is that once you collect that data and find out the actual stress state of the part, or the actual strain state of the part, you have to compare it to a finite element model to determine what are the actual parameters we're backing out of this system. When we started on it, this a single test took about 5 minutes. You ran 20 to 25 tests per sample that you were studying on one loading condition. And then you would run dozens of loading conditions, dozens of composites, all with 25 replicates in order to create enough data to be able to start figuring out what was going on. To process the test results for one sample took about 5 minutes. Took 5 minutes to collect, took about 24 hours to actually process the data. So we figured out how to create a surrogate model that replaced the finite element model. And in the first year, we took that 24 hours down to 5 to 10 minutes. We learned a lot doing that. And NRL was very excited about that. We can now process the data almost as fast as we can collect it. So we said we thought we could do better. We learned from that surrogate model more what the characteristics were needed in the surrogate model in order to effectively represent the problem. So we came back a year later, with a new variation of the surrogate model customized for this application, took the runtime down from 10 minutes to about 30 seconds. NRL's pleased. So we're down to the point where now the limiting factor really is the test itself. We thought we could do better. Third year, we come back, we parallelized some of the code, improved the hardware a little bit using GPU algorithms, dropped our analysis time down from 30 seconds to about 50 microseconds. This was a huge, or 50 milliseconds, which was a huge advantage because we got in the control loop of the experiment. So now, while we were testing a single coupon, we could determine if we reached statistically significant data to converge on what the answer was before we completed breaking the coupon, which meant we could use one coupon and conduct multiple loading tests on it because we could just move from one loading condition to another loading condition and continue collecting data. Some of these coupons were $1,000 each, so you can imagine the amount of money that gets saved in terms of being able to get multiple tests out of a single coupon. So this led us to the first law of surrogate models, that while I'm certain it went in and I'm certain it comes out, all I can be certain of is that I'm certain there's some uncertainty going into this as well. So how are we going to deal with some of the uncertainty issues that are present within the data we want to process? Well, we've used this for different analysis approaches where we've had to deal with uncertainty. We've worked with robotic path planning, manufacturing planning, condition-based maintenance prognostics, as well as Monte Carlo system assessment, basically making small data into big data through this process. And I want to highlight a project that one of my master's students did. She showed up at my doorstep when I was assistant professor at the Colorado School of Mines. She was a runner and found out she had a degenerative spinal disc condition and was going to have some spinal discs replaced by the time she was about 40. So she all of a sudden got very interested in how to design spinal disc implants. It turns out that's not a simple problem because you design the implants, but you have to design them to be satisfactory across a population of people. So now you got a lot of statistics that come into play. She built a functional unit test model for that spinal disc implant, developed a high resolution and low resolution models. But part of the process was that we have to run a Monte Carlo simulation to look at how this design works within a population of individuals. And the Monte Carlo simulation could take a fair amount of time. We found out we could actually represent individual spinal disc models from their finite element simulations pretty effectively with some surrogate modeling techniques. We could even use low resolution models to effectively predict high resolution models with reasonably good accuracy, although some level of uncertainty involved. But most importantly, well, it takes 23 minutes to run an individual finite element model of one of these disc implants. We found out we could actually build a surrogate model of those set of models with about 10 samples, so a little under 4 hours, fit that surrogate model in about another 6.2 minutes, and then run a 1,000 sample Monte Carlo, the standard that was used by many of the companies designing these implants, to tell us whether or not the design was a good idea or not, in a grand total, including the original model construction, of about 8 hours. If you do it the old way, primarily through finite elements and Monte Carlo simulation on a finite element analysis, that same iteration took 16 days. So design iterations on a day basis as opposed to a 2-week basis. Quite a bit of power from the surrogate models. So my second law of surrogate models is that you don't know it all, you can't know it all, yet you have to make a decision only based on what you know. And so we have to do a lot of decision making where surrogate models can be useful. And that's led us to use surrogate models as a component within a number of artificial intelligence agents, looking at intelligent traffic lights and how they might interface with autonomous vehicles and what I call non-autonomous pedestrians. There's a number of interesting collaborations and connotations that are possible when you start merging these technologies, because you can work with very small data sets and you can learn and adapt these models as new data is collected from the system. So another grad student I had decided we need to do some robot path planning. With a robot that basically would take off, fly a distance, and then find a landing zone and land in it on Mars. Now, he did this long before Ingenuity started flying around. He did this kind of as a conceptual exercise. The question is, how do we balance the uncertainty in that flight? We know we have some resolution of data. In this case, we had 10-meter resolution data from HiRISE. But we also knew that we would have locally informed data from this robot about the landing zones. And so the goal was, how do I decide where to fly to get between a starting point and a destination, which gets me there as efficiently as possible, but balances the uncertainty of whether or not I can land in between. So knowing we couldn't make it in one flight, what happens? How do we make that planning happen? So we built surrogate models that looked at both the analysis of the low resolution initial model that was then informed by high resolution data based on what the robot could see around it and during its flight path. The longer the flight, the less elevation the robot got, so the less it got to learn about the environment around it because it couldn't see as far. The shorter the flight, the higher the elevation the robot could get to. So we built these models of a section of Mars and started having the robot fly around on Mars. And these are some of the path plans that you see it get. It decided to transverse up and down a valley between the starting point, basically following a reasonable path through the valley. It found the low point out of a crater and over a ridge to get to the valley, and found a low point to get over a ridge and into a crater going the other way. But what was really unique was there were cases where it decided, I don't know where to go. And so what did it do? It went up as high as it could go and landed where it started. This was behavior that was not programmed into the control loop of the robot, but came out of the surrogate models. The best thing it determined it could do was find out more about its surroundings. And so we found emergent behavior coming out of a real basic system, real basic set of surrogate models that told us a great deal about what was going on and allowed us to adapt to situations. And so we've learned it's surrogate models all the way down within the system. And we think surrogate modeling is a great technique. We look for collaborations where we can apply this to help solve other problems. Any questions?
On the disk problem, how does one go about validating those models? What is the measurements and you take to calibrate it?
So what we started with is we would start basically with one disc between two vertebrae, and we would use the kinematics of the back to provide different loads that were typical of what are experienced by vertebrae that are kind of known on the disc, and look at how the disc deforms under those loads and whether or not it provides acceptable deformation so as not to impinge upon the spinal cord. But we have to do that across people across the population because we all have different sized vertebrae, and yet no company is going to make one custom for a particular patient. They're going to make one that has to work across the population. So a lot of that's done on cadavers, but there's enough data out there for us to do a lot of finite element modeling initially to basically determine whether or not we have a candidate disc that we can then study on a biological specimen. And ultimately, after it proceeds through this design phase, it would go through medical trials on voluntary patients.